Galileo is credited as being the first person to use a telescope for astronomical observations, so back in 1610. He actually didn't invent it. It was a Dutch kind of optics experimentalist who invented it a couple of years earlier. And there are some claims that there was a British astronomer who made astronomical observations with a telescope before Galileo, who's Italian. But records are a bit vague. As an astronomer, you should know about Galileo's famous observations. And he was using a telescope that was way worse than the 16-inch telescope, much worse, much smaller field of view. This was very challenging. But he was still able to see mountains on the moon. He was able to make out that Venus has phases, which is a really important piece of observational evidence that the Earth goes around the sun, not the other way around. He could see ears on Saturn, and so this is one of his sketches of Saturn, and the rings to him look like little ears. And he tracked the motion of the moons of Jupiter over time, and also observed sunspots. So it's really would be easy thing to do to track the motion of the moons of Jupiter over a period of time with our telescope. You should absolutely be able to see the phase of Venus, the current phase of Venus, and you can see beautiful rings of Saturn, and the moon is fantastic. The moon is 1/2 degree by 1/2 degree, so it almost exactly fills our CCD, so it's beautiful. Okay, so there's two main types of optical telescopes. There is what we call a refracting telescope, which is kind of every sort of children's view of what a telescope looks like is a refracting telescope. This would have a lens at the end of a tube, and that lens then focuses the light, which gets expanded back out into your eye using an eyepiece. Galileo's telescope was a refracting telescope. There are problems with this kind of telescope. So most modern telescopes are now reflecting telescopes, which instead of having a lens has a mirror. So one of the issues with lenses is that, as you remember from optics, right, the refractive index depends a little bit on wavelength. And so the focal position of different colors will be in a different place. And so you end up with stars not looking like single points, but getting spread out, and you can see a little sort of color kind of halo around them. That's called chromatic aberration. You also can't make them super big. Think of the giant refracting telescope in the classroom at the observatory, right? That's really, really long in order to make it big, but making it much bigger than that, and you have kind of lots of structural problems. So reflecting telescopes with mirrors, which can be near the center of mass of the tube, are a good solution. Our 16-inch telescope is a reflecting telescope with a pretty similar setup to this. Instead of having this secondary mirror focus the light off to one side, it focuses it back through the central mirror, and you put the eyepiece down at the bottom. Okay. So there's a bunch of telescope terminology that I wanted to go through. Again, these are sort of terms I picked up out of the chapter of the book that goes through this. So I already talked about refracting and reflecting telescopes, but let's go through the rest of these terms. So let's start with the aperture. It's the diameter of the main mirror or lens. So let's use D. For our 16-inch telescope, it's 16 inches. So often telescopes are labeled by their diameter. So for example, one of the first telescopes I used as a graduate student was a 200-inch telescope, 5 meters diameter. And professional astronomers these days are building 8-meter telescopes, 10-meter telescopes. Really, they're really big, really, really, really big. 16 inches is big for the kind of telescope that we can have on a campus. I think Swarthmore has a 20-inch, possibly 24-inch. You can get bigger ones, but what we have is 16-inch. Okay, how about focal length? So if you have a refractor, it's going to be the length between your lens and your focal point. So if we call it F, I've drawn a lens. It's the same thing for the mirror. It's the length between the mirror and the focal point. We often bend the light. So in our telescope, in the 16-inch, it's all bent around. Believe it or not, the focal length of our telescope is 4 meters. It's 160 inches. The other thing we often talk about with telescopes is the F ratio, or the F number. This is the ratio between the focal length and the diameter. So both of our telescopes are F10. So you don't need to remember the focal length is 160 inches. If you remember that it's F10. Meade just makes a series of F10 telescopes. It's a really common focal or F ratio for telescopes. Okay, and then magnification. What is the magnification? Not as in what is the number, but what functionally is the magnification?
Like how many times it enlarges the image?
Yeah, exactly. So like mathematically, we could say it's the ratio of the angular size, that's supposed to be an E, sorry, of the object to its like apparent angular size in your eye. So I put a little video that I made in Explain Everything on Moodle where I go through the math of this. It's pretty simple trigonometry. If you draw a basic picture of a telescope and do some trig, you should be able to convince yourself, and I go through this in the video, that magnification is equal to the focal length of the telescope divided by the focal length of the eyepiece. So it ends up being 2 triangles. So you have this sort of triangle like this, where this is the focal point, this is your lens, this is your eyepiece. Those 2 angles have to be the same. And you can end up convincing yourself this is what the magnification should be. Oh, and a warning here, there's an error in the book here in this equation. So if you get confused, that might be because you found the error in the book. Okay. Oh yes. So the next picture here is the one that I used to go through the calculation of why it makes sense that magnification is the objective focal length, or the main lens focal length over the eyepiece focal length. So that's why the magnification, if you've ever been for public observing, I put it on the eyepieces, not on the telescope, because it depends on the eyepiece, not the telescope. Well, it depends on the combination of the two, but we don't change the telescope, we change the eyepiece sometimes. Okay, we're not going to put eyepieces on the telescope, so the equivalent for us is going to be the plate scale, which again, the book will go through how to calculate what that is. Okay, so that's the magnification. Angular resolution is important too, though. So what's angular resolution? So the minimum angular separation that you can distinguish. I have a picture on the next one. Yeah. So here are my 2 blobs, and as we move them closer together, they turn into a single blob. And, this is the ultimate resolution of a telescope is set by the diffraction limit. So we're back to optics. And you probably calculated the diffraction limit of a circular aperture at some point in optics, and it's 1.2 lambda over d. It probably won't shock you to know that many astronomers ignore the 1.2 and just say the angular resolution is lambda over d. 1.2 is 1 to many astronomers. You can use 1.2 if you prefer. Won't make that much difference. Okay, but that's the theoretical resolution. You only get that if you're in space, or if you're the Hubble Space Telescope, or if you're a radio telescope, we get that too. So that's cool. That's because the wavelength of the light is large compared to the atmosphere. In optical wavelengths, we have to worry about seeing. That really sets the resolution. So what's seeing? Yeah, so it's a measure of atmospheric turbulence. I like that. It basically is effectively the smallest object, or the smallest separation you can resolve. Because of this sort of turbulent mixing, it kind of blurs everything out. Basically, stuff looks blurry. your eye, you pick this up like as twinkling stars. Stars twinkle because they move around slightly in the atmosphere because of this turbulence. In your CCD capture, that's just going to blur it out, right? And then I wrote here PSF, which stands for point spread function, and a full width half maximum, just because these are terms you will read about seeing. Full width half max. If you imagine sort of scanning across your image and getting the intensity in one direction, you might get like a little sort of hump around your star. The full width half maximum is the width of that hump at half the peak, just like it says. And the point spread function just is the full functional description of the shape of that. So I notice I carefully said it wasn't Gaussian. Like many things, it's approximately Gaussian, but it's not precisely Gaussian. And if you want to have this really precisely, people will model these things very precisely. So the full shape of it is the point spread function. We already talked about refracting and reflecting telescopes. Space vampires, yes, how to tell if there are space vampires or not. Have a refracting telescope, not a reflecting telescope. It's an XKCD joke for anyone who doesn't know. The other term is equatorial mount. And here, I'm going to draw the Earth at an angle. So this is going to be like north and south. Here we are in Haverford at like 45 degrees latitude. And we want to have a telescope that's easy to track the stars with. And so what we end up doing is lining it up so that its axes point north. So if you were to point the telescope along its main axis, it's pointing north. And then the other it rotates around with the stars, and then it rotates up and down relative to the equatorial grid, not relative to the ground. That's why it kind of looks funky and it's at a weird angle. That kind of telescope is much easier to point as a person. Believe it or not, you might not believe that, but it is. The alt-as ones are more popular in modern observatories because they just get pointed by a computer, and the computer does all the calculations for tracking. Our telescope, you could track it with a clockwork mechanism. For tracking, it only has to drive around the RA drive to follow stars. I think that's all I wanted to say about telescopes. This is not everything you would ever want to know about telescopes, but this at least hopefully will get you started. So now let's talk a bit about the detection of light in astronomy. We will not escape magnitudes, so I wanted to remind you of the magnitude system, which I'm sure you love and remember from your astro class. So remember, magnitudes are a ranking system. So the brightest stars that you can see with your eye were ranked number 1, magnitude 1, and then the next set were 2, and the next set were 3. So that means it's a reverse scale. Bigger numbers mean fainter stars. And it turns out that our eyes are a logarithmic detector. So sort of the next set, it turns out, are 2.5 times dimmer than the first set. This guy called Pogson figured this out in the 1800s. And thanks to him, we can continue to use the magnitude system in the modern era with empirical measurements of things. So he figured out that the difference between two magnitudes was 2.5 times the log of the ratio of their fluxes. So for observational, this is the main magnitude equation you might want to remember. All right. I thought that we actually would have a bit of a chat about the eye at this point. And I looked up some of this stuff because I wanted to add this in. This is my astronomy version of how the eye detects light. So I apologize to anyone who's taken biology more recently than me. But your eye, in your retina, you have a bunch of light detecting cells, and you have 2 types actually. You have something called rods and a type called cones. So according to this image, your cones are mostly in the center of your eye, and then the rods are around the outside of your eye. And the rods are much more sensitive to light than the cones. So the side of your eye is more sensitive to light than the very center. In astronomy, we call this averted vision. So if you want to see something faint, sometimes you try and look at it from the side of your eye. You should be able to detect it with your eye better than if you look at it straight on. But the other important difference between rods and cones, apart from the sensitivity, is that rods can only see monochrome. They are not sensitive to color. So when it gets dark out, you don't see color anymore. The cones are sensitive to color, and the way they do that is there's actually 3 different types of cones. So there's like a red detector, a green one, and a blue one in your eye. And they detect, they have different sensitivities to wavelength, and your brain puts that together as a color image. So this was a chart I found showing the range of sensitivity of your eye. So your blue cones, your green cones, and your red cones, they get added together to make a color image in your brain. Cool, huh? So a lot of cameras are color cameras, and the way they do that is they have multiple pixels. So they have a red pixel, a green pixel, and or maybe 2 green pixels, and a blue pixel next to each other, and they detect them. In astronomy, we try to avoid doing that because we lose pixels. You have to have like 4 pixels for every resolution element. And also you lose sensitivity doing that. So we use this type of camera called a charged coupled device, or CCD camera. But they're very broadly light sensitive. They're actually sensitive to near infrared right through to ultraviolet. And so if you just take an image with a CCD, you just get a monochrome image with a very broad sensitivity. So what we have to do if we want a color image with a CCD is put filters in between the path of the light and the CCD to limit what passes through, and basically then have it act like our eye and take images in sort of red, green, blue and put them together later. So these are some common filter sets that you might see in astronomy. So 2 people named Cousin and Johnson figured out this set of filters and sort of came up with a standard set. We like to use a standard set for calibration. So it means that we can look up observations that have been done through these filters in the past. So you see this is U, B, V, R, I in capitals. Roughly UV blue, visible red, infrared. This lower set is the set that was developed for the Sloan Digital Sky Survey, which you know that I'm heavily involved in. And because SDSS made so much imaging, this has become a sort of de facto standard for a lot of astronomy. So you'll see this one a lot. And here we use lowercase U, G, R, I, Z. So again, U-band, green, red, infrared, and this is a little bit longer infrared. You might also see very narrow band filters. So we might pick out the emission that's just from specific emission lines. So some really common ones are oxygen 3, hydrogen alpha, silicon 2, and nebulae. So like the ring nebulae or the helix nebulae, you know, ionized gas creates lots of emission lines. And so they can have some really interesting colors if you look at emission lines. Remember, I don't know if you remember, but I will remind you that the hydrogen alpha line traces star formation in galaxies, because you'll see like little blobs of it in places where stars are being formed in a galaxy. So a H alpha image of a galaxy actually can be pretty cool scientifically and visually. And Kevin, was that you speaking?
Yeah. I was just wondering what's causing the skewing in the graphs on the right, on the 2 graphs on the right, and is it like something like especially the one on the top, like the standard one, like is the skewing something that was intentionally put there? Or
so I think so you'll see a mixture of ways these filters are presented. Sometimes they're presented sort of with uniform peak sensitivity, and that might be how they're built. But we also look at stuff through the atmosphere, and so this curve actually has the atmospheric transmission on top of it as well. And our atmosphere is not as transparent in UV and infrared. And so that's why these are lower. So this is the actual like sensitivity to objects that are outside the atmosphere that you get from those filters. And so I've been a bit loose here because this one here it's at 100%. So this is a laboratory measurement. This is a laboratory measurement, and this is through the atmosphere. The weird wiggles should give you a sense of that too. Cool. Okay, so this is the post-it note that we shall not lose that is on the control room computer that says which slot in our filter wheel has which filter. So you see we've got B and V from Johnson Cousins, we have GR and I from SDSS, and we have H alpha, oxygen 3 and silicon 2. So you can do GRI imaging, which is the standard Sloan imaging. So this is going to be beautiful for galaxies or for planets. You can do emission line imaging. So for a nebulae, for example, you might do a clear one, so let as much light through as possible to get a beautiful grayscale background, and then put on top color from different emission lines, so you can tell where the hydrogen and the oxygen are in your nebulae. There's not really a right answer. You could try GRI imaging of a nebulae, and that would be perfectly fine. You could try using emission line imaging on a planet. There might be something interesting going on. Rocky planets, probably not. But like gassy planets like Jupiter and Saturn might have emission line stuff going on. Galaxies also. One of the challenges with the emission line filters is they're very narrow. They don't let a lot of light through. That can be good because they don't let a lot of skylight through, but it also can mean you need longer exposures. I recommend always taking 3 images in each filter. Take a short one first. If you don't see anything, take a longer one until you see something. And then take 3 of the one that worked. And then, so my plan for Monday is to talk a bit about how to combine images taken through filters to make color images. So your screen each pixel has 3 color little lights effectively. And if it wants to be red, it sends more signal to the red light and less to the blue and green. This is called the RGB system for red, green, blue. So your 3 images, so you're going to take 3 in each filter, but then you're going to take 3 filters as well. You're going to combine the 3 in each filter together to add them up. And then you're going to set one of them to be in the red channel, 1 green and 1 blue, and make a color image. And I'll show you how to do this, so you don't need to know how to do it right now. This wheel here is supposed to illustrate, so it's got RGB in these sort of outer bits showing, adding blue to green. It's like art class again. I used to like this stuff when I was in school. It's fun, right? So we get to do it with astronomy images.